An electrocardiogram or ECG amplifier with right leg drive is explained in this video, which is the 209th example in the circuit analysis playlist. For one channel, the two electrodes left and right are connected to the patient's arm, and then ECG signal is picked up and then fed to the positive or non-inverting input terminal of 2 op amps as shown, and then we are supposed to, or we expect that the circuit amplify the desired signal, and then at the output we sample the undesired common noise, and then we try to feed back that noise to the right leg to get rid of it to a very good extent possible, basically improve the common mode rejection of the circuit. So this is the big picture of how this circuit is working, and now we want to see what are the voltages and the details of operation of the circuit. Okay, so in ideal ECG operation, if there was no noise, then what we expect that electrodes connected to left or let's say to right arm supposed to pick the red signal that is shown here, which is the actual ECG signal. But then the truth is, because the body of patient effectively acts like an antenna that picks up the 50 hertz or 60 hertz main power interference, because of that, we have a substantial, so I'm going to write 50 hertz in Europe and Asia and 60 hertz in North America. So because of that, we have this effective blue noise that is on top of the actual desired ECG signal and can be pretty powerful. So actual desired ECG signal could be on the order of, say, a few microvolt, that's the level, while the interference, the 50-60 hertz main power interference, can actually be pretty sizable. On a side note, in addition to the interference, we also suffer from a movement noise, which is a low frequency, or say on the order of 0.5 hertz noise on average, which is there effectively because of just the patient movement or electrode movement. So you can see that the center of this whole let's say sample signal, which has a sizable 50-60 hertz on top of ECG, is also moving or sort of moving along on a sort of a varying low frequency varying noise, which is the motion noise. Okay, in this example we are talking about getting rid of the common noise, for example the 50-60 hertz noise which appear on both electrodes. Okay, so if we were only dealing with the differential signal, which is the desired ECG signal, then we would say, okay, the differential signal appeared, say, between the positive terminal of op amp 1 and op amp 2, in the sense of we have V in, let's say, in this case, we have V in, let's say, 2, and we have V in 1 connected via these sizable resistors, or just for the sake of impedance matching. And then we have V in 2 minus V in 1 appearing as our delta. So we have V differential, which is the desired signal, ECG signal, V in 2 minus V in 1. And because the 3 op amps in this circuit properly bias, so if we have plus minus 10 volt or plus minus 5 volt supply, it's connected there, for example. And we have negative feedback in place. As you can see, output of op amp is connected via the resistor R1 to input an inverting negative terminal indicating negative feedback. So because of proper bias and negative feedback, we would say the op amps are properly operating, and because of that, op amps are in linear region of operation, and therefore virtual short is enforced via negative feedback, which means the voltage at positive terminal of the op amp should be equal to the voltage of negative terminal of the op amp, referred to as effectively virtual short for the properly operating op amps in linear region. Okay, so what is the meaning of that? V in 1 is at positive terminal, so obviously V in 1 should be at negative terminal as well. V in 2 at positive terminal of a properly operating op amp, so V in 2 at negative terminal as well. Okay, so effectively the V in 2 minus V in 1 is across the series of 270 ohm and 10 kilo ohm potentiometer. The 10 kilo ohm potentiometer obviously is adjustable from 0 to 10 kilo ohm. So effectively the series resistor here can be as low as 270 and as high as 10.27. Okay, so what I can say is, if there is a current that is flowing through, let's say, here is the current. So the current I, let's say I1, is flowing because of the differential voltage is flowing through the series of these resistors, and then that current cannot go to the input of op amp because effectively input of op amp has infinite impedance, so it can continue only this way via R1 and to this point, and it can also come this way and cannot go through the input of op amp, can go that way. So what I can say is, as a result of this, I can say, let me just write it here. I can say I1 is equal to the current V2 minus V in 2, which is the V differential effectively, V in 2 minus V in 1, that's the V differential, divide by, so I'm talking about the voltage across these two resistors, so divide by the value of those two resistors. So it would be, let's say RP, RP meaning that the resistance of potentiometer, that's the 10 kilo ohm potentiometer, plus the fixed resistor, which is the 0.27 kilo ohm or 270 ohm. So that's the I1. Okay, this I1 is now flowing from Vout2 node, which is the output of op amp 1, as was shown, and then go through the series of all the resistors to get to Vout1. So what I can say is Vout2 minus Vout1 is equal to, I would say, the current I1 times the resistors we just discussed. So it would be R1 plus 0.27 kilo ohm plus RP plus another R1 in the return route. So R1. Okay, substituting for I1 from equation 1. So I'm going to substitute for I1, and as a result I get Vout2 minus Vout1 for differential voltage is equal to and instead of V in 2 minus V in 1, I'm going to just write V differential as I mentioned on top, basically the desired ECG signal. So it would be V differential divided by, that's for I1, RP, the potentiometer, 10 kilo ohm potentiometer, plus 0.27 kilo ohm. And then numerator, we have 2R1, so it would be 2R1, which is 2 times 27, because R1 is 27 kilo ohm. Okay, so 2 times 27 kilo ohm, and plus 0.27, which is this guy, and finally RP. Okay, so as a result, we find that the differential output voltage in the presence of desired differential input signal, V differential, is just equal to, so I can write it this way, or I can just simply say divide by V differential, or basically the differential gain. So let's write it this way. Differential gain of this circuit or ECG amplifier for the desired signal is just equal to now the whole thing that is written here. So it would be RP plus 0.27 kilo ohm plus 2 times 27, which is 54, divide by RP plus 0.27 kilo ohm. Okay, so at minimum RP is 0, and at maximum RP is 10 kilo ohm. So we can find the range basically in this case. If it is 0, what we're going to get, basically if RP is 0 for this amount of gain, we are going to get on the order of, say, 1 plus, and we have 201 basically, so roughly 200. And if RP is max 10 kilo ohm, so we're going to get then, we're going to get effectively on the order of roughly 64.27 divide by, and then we have 10.27. So that amounts to on the order of, say, about 6 point something gain. So That's the lowest gain we're going to get in this circuit when RP is set equal to 10 kilo ohm. And the highest gain is obviously, as shown, is on the order of 200 roughly. Okay, so that is for desired signal. But so basically, that is the gain observed for the desired signal in red. But then how can we get rid of the undesired or unwanted signal in blue, which is the common signal that is picked up by both electrode on the left and right arm? Okay, so we refer to as V common mode. So I'm going to write it here. V common mode appear positive terminal, V common mode appear negative terminal, as we can see here. But then because of virtual short property of the two op-amps, that should appear at the negative terminal as well. So basically V common mode as a result of virtual short will be, I'm gonna just remove I1 that I just wrote here. So we all know that as, let me just make sure that I1 is captured. Okay, so I1 was here. I just said that V common mode appear at the two side of the 270 and 10 kilo ohm. So effectively what happens is there is no current flowing, and as a result, since no current flows through these resistors, the two op-amps for common mode signal behave like a buffer. And therefore this V common mode, since there is no voltage drop because of the VCM or V common mode across R1, appear at these terminals as well. So V out, the contribution of common mode, let's say voltage, using superposition, as if we just dealt with V in 1 and V in 2 separately. Now we are dealing with the common mode voltage. So common mode appears at both V out 2 and V out 1. So let me write it here. Okay, so since common mode voltage appears across both of these 27 kilo ohm, effectively from perspective of common mode voltage and the rest of the feedback network here, what we have is we have this situation. So we have V common mode and connection via 27 kilo ohm. And we have another 27 kilo ohm, which is the lower one, this guy, connected to V out 2, which is effectively V common mode again. So that would be V common mode. And V common mode, as I said, I'm referring to the common 50 or 60 hertz example of interference picked up from the main power. Okay, so this is connected to, as you can see, the center, the mid node is connected to the input negative terminals of op-amp number 3, which is the feedback op-amp in this network. Okay, so one interesting thing as well is for differential voltage, because V out 2 is going to be, for example, equal to just exactly the negated version of V out 1. Therefore, since the V out 1 and V out 2 are exactly negated version of each other, the center node will be 0 for the differential mode. So basically, ideally, the differential signal doesn't contribute anything to the input of this feedback network. So the only input appears would be V common, as I showed you. Differential or desired signal is not contributing to the feedback network. So now we have, so op-amp number 3, and I'm going to show it this way. So this is op-amp number 3. The positive terminal is grounded. The negative terminal in an inverting amplifier fashion with a low-pass filter. So we have 4.7 nanofarad here. And we have 270 kilo ohm. And then the output, which goes to a connector resistor 270 kilo ohm, and a sort of a stabilizer cap, which is on the order of usually few tens of picofarad, connected to the green cable here. So I'm going to show it in green. Connected to the green cable, and then that goes to, just showing it here, that goes to the, to drive the right leg of the patient. So it goes to the right leg. Okay, so what's the big deal here? So the big picture is, as I said, first, only common mode voltage interference, common interference will contribute as non-zero voltage at the input of this feedback network here. So differential signal doesn't contribute anything. On the other note, please note that the combination of, usually what happens is the combination of the resistor and capacitor in this feedback in this feedback amplifier form this RC, form a low pass filter that if we compute the omega, so I'm going to compute the omega for this RC here. So omega RC is equal to 1 over RC, or effectively I can say the frequency of 3 dB or cutoff frequency for the effective low pass filter is 1 over 2 pi RC, where R is 270 kilo ohm in this example and C is 4.7 nanofarad. If we compute this, it turns out to be about 125 hertz roughly. So what's the benefit of that? The benefit is so any higher frequency, let's say signal, common mode signal above this is not going to be effectively fed back via this feedback network, which is a good thing because usually the common mode undesired signal or noise because of main power contribution is on the order of 50, 60 hertz-ish or frequencies in that ballpark, nothing above 100 or 125 hertz normally. So that's one good thing about setting the RC values here. The other one is the C here is usually set on the order of tens of picofarad. It's a stabilizing cap just to make sure circuit remains stable. The 270 kilo ohm at the output of this op amp is mainly for limiting the amount of current on the order of say microamps or even less to drive the right leg of the patient. So with that said, let's just compute effectively this inverting amplifier that we have here. So since we have V common mode, this 27 kilo ohm is actually going, which are the resistors that we have here. They are going to actually be in parallel effectively. So I'm going to say the feedback gain is equal to, this is an inverting amplifier. So the feedback gain below the 3 dB cutoff frequency, so when I can neglect the 4.7 nanofarad, is simply negative 270K divided by half of 27 kilo ohm. So it will be negative 270 kilo ohm divided by 27K divided by 2. So in this example, set up this way, effectively we end up with gain of negative feedback to be on the order of minus 20x. So that's the feedback gain, let's say voltage gain. So what is the benefit of that? Effectively, what I showed you is if there is a common mode, let's say signal picked up, as I showed, the gain of the feed-forward amplifier from input to output is 1 for common mode. So V common mode appears at input and then it shows up at the output as it is. And then of course whatever voltage appears here, we are effectively driving the voltage into an A to D or analog to digital converter in order to digitize it and for further post-processing in digital domain with whatever processing we want to do. So the feed-forward gain is 1, so effectively I can think of the circuit for common mode as if we come here, and this is the point that using the right leg we are driving the right leg via this green connector. So we are driving back the amplified version of common mode via the feedback gain, which is in this case gain of 20 negative, and the negative 20 is just reflected here. So here is the body of patient effectively. So patient's body. And we are trying to cancel out the effect of the common noise by just driving the right leg, and here is the gain of 20 and the feed-forward gain is 1, and here is the common mode voltage at the output, so or basically the output voltage, let's say V out for common mode. Okay, so this is a classical feedback system. We know that in the classical feedback system, V out common mode divided by V in common mode, let's say, is equal to just as simple as this gain divided by 1 plus the loop gain, which is 1 times 20. So it will be 20. Effectively, if this gain is A, then we would have 1 over 1 plus A. So in this case, it's 1 over 21. That's the beauty of this network. Basically, with this design, what happens is, effectively, the gain of the circuit for the common mode undesired voltage is 1 over 21. See what happened? It means that the blue undesired 50 hertz or 60 hertz common mode noise or interference that appears on both electrodes will be attenuated by a factor of 21 in this circuit because of the proper design for the feedback that is driving the right leg. So effectively, V common mode will turn out to be, with the feedback network, will turn out to be attenuated by a factor of 21. And what happens is then the actual desired signal, differential signal, which is the red one, is actually going to be amplified by, depending on the setting for RP, as high as 200 times or as low as, say, about 6 times if we set RP equal to 10 kilo ohm. So this is just the gist of overall performance or operation of the circuit and how it works in terms of amplifying the desired differential signal for ECG and removing the undesired common noise or interference. Of course, there are many nuances in actual implementation. Electrodes, they have their own passive equivalents in terms of resistor capacitor. The cables themselves, the blue and the red cable here, they also have their own resistor, net resistor cap, let's say, equivalent, or basically passive element equivalent. So extra care must be taken into account to practically design a proper ECG amplifier to make sure that the circuit is stable as well. But this is the overall view of a good example of, let's say, ECG amplifier with right leg drive. I hope that this example is interesting and helpful. Thanks for watching.